Okay, so part two for today. I needed a break. You probably needed a break. Just a couple more quick examples on applications of the derivative, specifically using the derivative to say things about the tangent line to a function. So, first things first, remember when I say the derivative, the most important sentence in all of calculus is the derivative is the slope of the tangent line. It is the instantaneous rate of change. These are all things that mean the same thing. It is the instantaneous rate of change of a function. We use a special notation. We're going to call this f prime of x. And this is what we call the limit definition of a derivative. It's sort of like how people discovered derivatives. We're going to learn some tips and tricks, some shortcuts. Trust me, you're not going to have to do this every single time you take a derivative, but you do have to. It's like a rite of passage for calculus. You have to suffer through it for 2 days, and then you're going to want to kill me when I tell you how you can do this a lot faster. Maybe you even notice, sort of, if you do a few of these, you'll start to pick up on the trick. But I just want to focus here today on what the derivative says about a function. So on the left, we have the function f of x equals 2/3 x plus 3. And I realized when I made this video 10 seconds ago, I realized that I have the wrong function drawn here, but that's okay. We'll get some practice drawing it again. It's 2/3 x, not negative 2/3. So we're going to go up 2 over 3. Here's our 2/3 x. This is the correct function here. Again, I'm not trying to draw it exact, but this is 2/3 x plus 3. And on the left, I've got the work done out for finding the limit definition of a derivative. I would say definitely pause the video or look at the PDF of notes. Make sure you can follow along what's happening. Make sure you can see how x plus h is being plugged in. Make sure you see how x plus h is being plugged in for x. Make sure you see how things are canceling, but I don't need to walk through another one of those. You work all this out, the h's cancel at the end, and you get the derivative is 2/3. Not 2/3 x, just 2/3. That's because the rate of change of a straight line never changes. No matter what point you pick, it's always up 2 over 3, up 2 over 3, up 2 over 3, up 2 over 3. It doesn't matter what point you choose. The slope of the line tangent is the same thing as the line itself. It's 2/3. That's always the derivative. Versus if we take a parabola, if we take 1/2 x squared minus 2x plus 3, and we do the entire limit definition of a derivative, and it takes us 5 minutes and our hands hurt, and you say you hate calculus, but at the end of the day you get it, and you say, yes, the derivative f prime of x is x minus 2. That's because the derivative changes. The slope of the tangent line depends. Is it this tangent line? 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 It should change depending on what x is. And I'm going to pick 2 to show you really quickly how amazing this is. Let's say I found f prime of 2. Well, 2 minus 2 is 0. Look what I just found. I just found that the tangent line to this parabola at its vertex has a slope of 0. And I found that using the derivative. I could have said that without looking at the graph. That's going to be a super fast way to find where maxes and mins of functions are later in this course. Let's say I wanted to know, what is the slope of this line when x equals 4, of the tangent line when x equals 4? F prime of 4, 4 minus 2 is 2. Let's check. Does that check out? Up 2 over 1. Let's go do it backwards. If I connect those 3 points, holy cow, there is my tangent line. It has a slope of 4. And so what I really want you to take away from this is look on the left. The derivative is just 2/3. The derivative is always 2/3 because the slope is not changing. It's got a constant slope. On the right, with a parabola, the derivative f prime of x is x minus 2. It depends. If x is at 2, the slope is 0. If x is at 4, the slope is at 4. Or sorry, the slope is at 2. Just caught my error there. That slope should be 2. And so it's the difference between, do we have a constant rate of change or do we have a changing rate of change, whether or not our derivative has variables in it. So that's one thing I wanted you to notice. And then here's just one more, then key points written there, same thing. One more thing. If, and really this is mostly just algebra review, if I ask you to find the equation of the line, find the full equation of that tangent line, not just the slope, the full equation of the line tangent to negative x squared minus 4x plus 1 at x equals negative 1. The easiest way to do this is point slope form. Now, you've probably been robbed because in your STAR exams, like slope intercept form is a lot easier for people to graph, so point slope form sort of gets the short shrift. But point slope form is great because you don't have to do any work. If you have a point, meaning you have an x1, y1, as long as you remember point slope form, you can literally plug in to the formula x1, y1. And if you have the slope, you can plug it in for m. Y and x are the actual variables y and x. You're going to see what this looks like in a second. If I ask you to find the equation of the tangent line, you always need two things. It's called point slope form for a reason. You need a point and a slope. So first we're going to find the point where this line is tangent. Well, they want to know, what is the equation of the line tangent when x equals negative 1? So literally all we're going to do, we're going to plug negative 1 in, because if it's tangent, it's on the original function. We plug in negative 1, we do our math, we get 4, we can check on the graph. Yes, our point of tangency is at negative 1, 4. And again, what I want you to know here is the graph is to help you see this. You don't need the graph. You just plug in negative 1, you get out 4. Your point of tangency is negative 1, 4. The slope of the tangent line, SOT, is a little trickier. The slope of the tangent line is, from the most important sentence in calculus, the derivative. The derivative is the slope of the tangent line. So we can find the slope of this line by, again, not going to do all this out right now, but you can find the slope of that tangent line by doing the limit definition of a derivative. You take the derivative of negative x squared minus 4x plus 1. Turns out the derivative is negative 2x minus 4. The derivative is negative 2x minus 4. That's f prime. You plug in negative 1, because I want to know what is the slope here when I'm touching that graph once. You plug in, turns out the slope is negative 2. We'll check to make sure. Down 2 over 1. Looks good to me. Yes, that is our tangent line. It has a point of tangency at negative 1 comma 4, and it has a slope of the tangent line of negative 2. And here's why point slope form is great. Oh, I'm a little in the way. Here's why point slope form is great. What's the equation of that blue line? Point slope form says y minus y1, this should say SOT. Y minus y1 equals the slope times x minus x1. I go caveman here. I don't need to think about anything. Do I know what these points are? Y is the variable y. Y1 minus, what's y1? It's the y value of the point of tangency. It's 4. Y minus 4 equals, do I know the slope? Yep, just found that out. It's negative 2 times x minus x1, negative 1, x minus negative 1, or x plus 1, either way. That is a fully acceptable equation of the line. You might want to clean it up a little bit and say y minus 4 equals negative 2 times x plus 1, but that's it. That is the slope, or that is the equation of that line tangent at negative 1 comma 4. So to recap, final key points for today, things you need to be able to know and do eventually, right? This is hard. This is not going to click immediately. End of the day, you got to tell yourself, right? It's a hard test. If you get 60% of the questions right on the AP Calc test, we call that a 5. This is not easy, so don't feel overwhelmed here. Or if you do feel overwhelmed, know that it's fine. Number one, you got to know the derivative is the slope of the tangent line. Most important sentence in all of calculus. If you remember one thing 10 years from now, you're going to remember that the derivative is the slope of the tangent line. Number two, saying it's the slope of the tangent line is saying it's change in an instant. It's the instantaneous rate of change, the IROC, IROC. Number three, the slope of a secant line is an algebra 2 problem. It's the average rate of change in y over change in x. Easy, right? Not calculus. Things you need to be able to do. Number one, calculate the average rate of change using a standard slope formula. If you have 2 points, if you have an x1, y1, and you have an x2, y2, this is literally your slope formula if you're asked for average rate of change. Number two, find the instantaneous rate of change using the limit definition of a derivative. I'm not going to make you do this too many times, but I will make you do it a couple times so you can show me you understand it. That's taking the limit of f of x plus h minus f of x over h, the limit as h approaches 0. And finally, the last thing, find the equation of a line tangent to a function by finding the point of tangency and the slope of the tangent line and plugging into point slope form, which is the y variable minus 1 y coordinate equals the slope times the x variable minus an x coordinate.